last section of the book, we started with a function, and we looked at when it was equal to its Taylor series as a function. So we looked at the Taylor series as a function, defining, for each x it defines a real number by taking limits of the partial sums. But in that section, we started with some function that we already knew, like e to the x, sine of x, cosine of x, and then we produced its Taylor series and said, aha, this equals its Taylor series. In this section, we want to begin a discussion of using power series themselves to define functions. So you don't have to start with a preconceived or pre-given function. You use the power series itself. A lot of this will seem like overlap with the last section, but we're trying to get used to the fact that we don't have to start with a function and have something we're approximating well by taking partial sums and using Taylor polynomials, that you just start with some infinite series and it defines something that's interesting to investigate. The reason this is an important topic is there are lots of manipulations you can do with power series functions defined as power series, that just that say that for a lot of purposes you can treat these infinite power series just like they're polynomials that never end, as far as adding, subtracting, to some extent multiplying, differentiating, integrating. They work like they're big polynomials, or never-ending polynomials. So that's where we're headed. I need to, I don't know, a lot of this will seem like overlap with earlier parts of the book. We just need to make sure that we kind of have a rigorous foundation for what we're doing. So I want to once again define what it means for a sequence to converge. We have talked about this once or twice before, but just to make certain that we have it down before we really need it for what we're about to do, a sequence. You should know, we usually write a sequence as something like three that I want to use as examples. Something like b sub n equals 2n plus 1, where n is greater than or equal to 0, or a sub n equals minus 1 to the n for n greater than or equal to 0, or c sub n. And the index doesn't have to be n. In fact, I'm going to switch to k for reasons that I'll explain when I do it. Cn equals 1 over bn, so equals 1 over 2n plus 1 for n greater than or equal to 0. These are all examples of sequences. For each integer n greater than or equal to 0, 0, 0, but I could have started anywhere. I typically call the starting index m, but you can call that anything too. These are actually functions. You give it an integer greater than or equal to 0, and it gives you back a number. So a sequence is really a function, but it's a function that just takes on integer values, and integers greater than or equal to some starting value. So typically you would write a sequence as something like b sub n, where n is greater than or equal to m, but this is really a function, b of n. But this is very standard when you're talking about sequences. And then we want to talk about what sequences converge to. Now, we've had limits since differential calculus. The limit as x approaches something. Well, the limit as n approaches something is just like the limit as x approaches something, except you only let this go through integer values greater than or equal to your starting integer value. Aside from that, the definition of the limit looks the same as it did when you allow what we call a continuous variable. X was allowed to vary through kind of all real numbers. And these, now we only allow things to vary through integers. But aside from that, the definition of limit looks the same. So the limit, we write the limit as n goes to n. So you start with some sequence, b sub n, and n is greater than or equal to some starting index m. You say that the sequence converges to L, or that the limit as n approaches infinity of b sub n is L. So this is, we also say b sub n converges to L. What does this mean? It means that, well, you want it to mean when n is really, really big, b sub n is really, really close to L. But really, really close isn't mathematically rigorous. So you have to do epsilon and for all and there exists. So technically, this means, and we throw out an epsilon, just use a Greek letter just to be confusing. For all epsilon greater than 0, there exists an integer capital N greater than or equal to our starting index for the sequence, an integer capital N, such that for all little n greater than or equal to capital N, b sub n is within epsilon of L. So the absolute value of b sub n minus L is less than epsilon. This is just the rigorous mathematical formulation of when n gets really, really big, this gets really, really close to L. Then we say that the sequence b sub n converges to L. If there is no such L that bn converges to it, we say that the sequence diverges. And we've used this terminology a lot. The opposite of converges is diverges. So these sequences, for instance, what happens is n gets really, really big here. When n gets really, really big, 2n plus 1 gets really, really big. So the limit of this is infinity. Now, that doesn't exist. So if your choices are to say whether sequence converges or diverges, this one definitely diverges. But it diverges to positive infinity, and that actually contains more information than just saying it diverges. Diverging to positive infinity tells somebody the reason it diverges is because it gets arbitrarily large, as opposed to this one. As n gets arbitrarily large, there is no one L, no one limit that this gets closer and closer to. When n is an even number, this is plus 1. When n is an odd number, it's a minus 1. So this sequence just goes plus 1, minus 1, plus 1, minus 1, plus 1. It doesn't approach anything. It keeps alternating. So this one diverges, but it doesn't diverge to anything in particular, but you could tell someone it diverges because it alternates between plus and minus 1, but you don't always say exactly why something diverges. There's just no limit that this approaches. Here, finally, here's one that converges because as n approaches, gets really, really big, 2n plus 1 gets really, really big, but 1 over that gets closer and closer to 0, so at least this one converges. The limit as n goes to infinity of the c sub n, that's 0. Okay, that's not too shocking. We've talked about sequences before, and we've used limits for a long time. We need partial sums, an infinite series, and this is something we looked at. We looked at this when we looked at Taylor series. First, we looked at Taylor series as formal kind of infinite polynomials that don't stop without defining functions. But in the last section, we looked at when they define functions that are equal to the original function that's giving us the Taylor series. But now we want to be a little more general, and so we just need to be careful. So we want to make sense of, so again, we'll start with a sequence, and now I'm going to subscript by k on the sequence because I'm going to use n for something else. So I've got some sequence of b sub k's where k is greater than or equal to m, and we want to make sense of the infinite sum. So the sum of all the bk's. This. Well, this shouldn't come as a shock to you given the work we've done in our earlier sections. What are we going to do? We're going to take the sum as k goes from m to n, where n is just some integer greater than or equal to m, and then we're going to take the limit as that n goes to infinity. So, and that's what it'll mean. So you just do this. You take the sum as k goes from m to n of b sub k. This we call the partial sum, there's a little confusion in terminology here. And we'll just try to avoid the issue. Would you call this the nth partial sum? Well, it's tempting because each m is staying fixed, and every time you change the partial sum you're talking about, all you're doing is changing this n. But that would mean you'd say something like the first partial sum. Well, first, I mean, maybe m's not 1, so you wouldn't want to say when n is 1, you get the first, or when n is m, would you call that the first partial sum? It gets a little confusing. So yes, if you, the point is, suppose your index starts at 2 and you go from 2 to 3 of b sub k. Do you call this the third partial sum or the second? Because all you're adding is 2 terms. And so the first partial sum would be this, the second partial sum would be this, but then the second wouldn't refer to this number up here. Anyway, it's confusing. So we'll just try to avoid it and talk about the partial sum, and if we had to call it something, maybe s sub n, or I'll use my script s so it doesn't look like a 5. You know, here's a partial sum, and we'll just avoid calling it first, second, or third. You take the partial sums, and you want to know if they approach something. So it's this. We would define, you define this infinite sum to be the limit of the partial sum. So here's a sequence. It's actually a sequence, because every time we change n, we get a new number. So I just called this Sn, but then I moved it. So, and if the limit of this sequence of partial sums exists, then we say the infinite sum exists. Or we say that this converges to whatever this limit is. And if this limit doesn't exist, we say it diverges. So an infinite sum like this is called an infinite series, or just series, an infinite series. It is a little unfortunate that series and sequence both start with an SE, and I don't know, somehow they get lodged in your brain next to each other, and people confuse the term sequence and series all the time. Sequence, it's just a list of numbers that never ends. The series is when you add them up. I didn't make up the terms, and it's unfortunate that they seem to be similar enough to people to be confusing. It's also important that you understand that there are two sequences when you talk about the sum of a series, or whether a series converges or not. There's the sequence of terms. So this is the sequence of terms. We call these the terms of the series. Terms of the series. So they're the summands, but summand's too long a word. So we usually say the terms of the series. They're the things you're adding up. But then there's the sequence of partial sums. And we're trying to make sense of the infinite sum, so it shouldn't be confusing. Whether the series, the infinite sum, converges or not is a question of whether the limit of the partial sums converge. It is not a question of whether the BKs converge. Certainly the BKs could converge and the infinite sum could diverge, and if you think about this correctly, this shouldn't really, this shouldn't get confused in your head. Suppose I take Bn equals 1 plus 1 over, or B sub k equals 1 over 1 plus k, and k is greater than or equal to 1. What's the limit as k approaches infinity of the BKs? So does this sequence of BKs converge? Yes. As k goes to infinity, this part goes to 0 and this part approaches 1, so this limit is 1. Unfortunately, that means that some students, sometimes people think that this infinite sum converges. No, that's so, think about what you're doing. This is a sum of the BKs, and the BKs are getting closer and closer to 1. But this is an infinite sum of the BKs, so it's like you're adding an infinite number of 1s. In fact, these things are always greater than or equal to 1, so you're adding an infinite sum of things getting closer and closer to 1, but all really greater than or equal to 1. But even if they were slightly less than or equal to 1, they're approaching 1. So this is like adding an infinite number of 1s together. This would diverge. Right? And what is it that's diverging? Well, the partial sums, these partial sums, this sequence of partial sums diverges because you're adding more and more things that are like 1 together as n gets bigger and bigger. So don't get these confused. It is a common source of confusion, and I'm not sure why. People confuse the BKs converging with the partial sums, the SNs converging, and this is why I switch indices on the sequences. I wanted to be able to use k for one index and n for the other index and not have them get confused. Okay, hopefully this is clear in your head already. What do we want to do with this? We want to apply it to power series. So for us right now, up until this point, we've looked at power series 2 ways, as kind of formal algebraic things that basically just consist of the algebraic expression that never ends. So it's just giving someone the coefficients in the center of the power series. And the other is we looked at them as defining functions, but only in the case where it was a Taylor series and it equaled the original function that gave you the Taylor series. Now we want to take the more general point of view, but this still shouldn't be too shocking for you. So suppose we have some power series, which we are no longer assuming comes from the Taylor series of something. Suppose we have a power series. P of x equals the sum, as k goes from 0 to infinity, of some coefficients times x minus a, so it's centered at some arbitrary a, to infinity. We want to know what this means as a function. Well, what do you think it means? It means what it meant in the Taylor series case, and it means what it meant when we were just doing series of numbers. It's, well, I can't seem to write a sigma. It's if p at some real number x naught, how do you define this? You define it to be the limit as n goes to infinity of what you get when you plug in x naught for x. So you take these partial sums. I'm writing x naught psychologically as meaning some particular x value. Here, x could just be some formal variable, but now I mean, okay, if you pick some real number, what we want to define this as a function. What does that mean? It means if you put in some real number for x, this should define some real number, and the real number that it defines is this limit, the limit of the partial sums. So it's the sum of the series when you replace x by your particular x value, provided this exists. Right? So this is the definition. It's the limit of the partial sums. The domain of the power series function. And by the way, we don't usually, almost no one says power series and power series function to mean anything different that's not kind of encoded in the context. If, in fact, we'll essentially always use power series as functions, and the fact that they're also formal algebraic expressions is fine. But at this point, you know, you look at a formal algebraic expression, and then you can ask, and yes, for which x naughts does it converge? So in that sense, there'll be separate things. There's this algebraic expression, and then there's when does this limit exist, and then when it exists, yeah, we define the function by this limit. That means the domain of the power series function is those x naught consist of those x naught for which this limit converges. So this is not too shocking. When does this define a function? Well, when you pick an x naught that you stick in here so that the limit gives you something that is defined when it gives you back a real number. So, right. This is our notion of a power series function. It's just the limit of the partial sums provided they exist. When they exist, the x naught that you plugged in is in the domain of the power series function, and if it diverges, it's not. So there's one point where you always know a power series function converges. So the real question is, for what other values does it converge? So suppose you have a power series function, or a power series, well, function. Suppose you have p of x equals the sum as k goes from 0 to infinity. Some power series. Okay, it defines a function and its domain is any x for which the limit of the partial sum, so when this infinite series converges. Are there any points in the domain? Is this defined anywhere? The answer is, well, it's always defined at least one point. Let me write out some terms of this. This goes c naught plus c1 times x minus a plus c2 times x minus a squared plus, and then keeps going. Well, are there any x values that we know this has to converge for? Yeah, the center. If you plug in x as a, all these powers of x minus a are 0, and you're left with c naught. So we know at least one point in the domain. Power series functions are always defined at the center. So we know that p of x converges at the center. It's always true. A power series always converges at its center, and it converges to, you put in x equals a, and what it converges to is just c naught. Okay, well that's easy. So the real question is, are there points besides the center where a power series converges? So we already know the answer to this is yes for a bunch of Taylor series, or in fact Maclaurin series. In the last section, and the one before that, we looked at Maclaurin series for various functions. In the last section, we actually talked about when they equal functions. So we know, for instance, from the last section, for all x, e to the x equals its Maclaurin series. So that's the sum as k goes from 0 to infinity of x to the k over k factorial. Yeah, we know that. Okay, forget that it's e to the x. Okay, I don't really mean that. Don't forget it. You should never forget this. Your whole life, you should remember this. But if we just ignore the fact that we had some function that we started with and use that to obtain this and that it equals this, in particular, what we're saying is this infinite sum existed for all x. So in particular, this power series function, this converges for all x. Now it's true that we know something, some function that converges to. It converges to e to the x. This function has a name, but my point now is that, yeah, here's some power series, and pretending that you don't know that it equals e to the x, it's still true that this function that this defines converges for all x. And we know the same thing about the series that defines cosine, which would use the even powers of x. So we had even powers dividing by the matching factorial, and the sign alternates. We know this converges for all x because, in fact, it equals cosine of x for all x, but in particular it converges. And what else? The series for sine. So you have the odd powers of x. And the sign alternates. We looked at least two series that converge not for all x, but certainly for x's beyond the center. We didn't prove these completely, although we proved for one of them that it converges for x's other than the center. We had the series for natural log of 1 plus x, right, which goes 1 minus x over 2 plus x squared over, let's try that again, which goes x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. It does this, well, ignoring that it equals the natural log of 1 plus x. So we've got this infinite series that is just the sum as k goes from 1 to infinity of minus 1 to the k minus 1, x to the k over k, no factorials. You've got this. What we said is that this converges and equals natural log of 1 plus x, but in particular it converges for x between minus 1 and 1. Now there's a slightly subtle point here, and that's why I'm looking at this as an example. In these other series for e to the x, cosine of x, and sine of x, we know that these series converge for all x. Why? Because we know, in fact, they converge and equal e to the x, cosine of x, and sine of x for all x. So in particular, they converge for all x. Here, on this series, we know that this converges to the natural log of, or we know because we said it even though we didn't prove it, that this converges to the natural log of 1 plus x as long as x is greater than minus 1 and less than or equal to 1. But, and it doesn't equal it out, well, it doesn't equal it out, well, you can't go any lower than minus 1 and have this make sense. And then, well, there's the question of, could this equality be true when x is greater than 1? And what we said was no, but the question that I want to address right now is, well, it's conceivable. Well, understand what we said before and what we didn't say. We said that this converges to that, so equals that when x is in this range. But it's conceivable, I'm not saying it's true, but it's conceivable that this series converges on a bigger set of x's, and it just doesn't equal natural log of 1 plus x. In fact, that's not true. But it doesn't follow from what we said before. All we were looking at before was whether a Taylor series or Maclaurin series equals the original function. We didn't look at the separate question of, is it possible that the function converges and doesn't equal, this converges and doesn't equal its Maclaurin series. Having said that, we did look at one example of a function that didn't equal its Maclaurin series at all, except at the center. This is a slightly different question of, yeah, this equals, this Maclaurin series equals the function natural log of 1 plus x on something other than center. Is it possible that this converges on a bigger set? So we looked at one example that's related to this, but just pointing out, what we've said before doesn't eliminate the possibility that this converges on a larger set. It doesn't, but we haven't proved that. We haven't said anything that implies it. Okay, but what about the series I just put up are all Maclaurin series of known functions. But what about, I want to use this specific example from the book, what about, just, I picked this example almost randomly in the book, but I want to write the same one on the board. So what about the power series x minus 5 to the k over 3 to the k times k squared? Right? I don't know of any nice function so that this is its Taylor series centered at 5. This doesn't have to be any the Taylor series of some nice predefined function. You can write out the first few terms if you want when k is 1. The reason we're not starting at k equals 0 is because we're dividing by k squared. When k is 1, you get x minus 5 over 3 times 1. And then you add to that what you get when k is 2. So x minus 5 squared over 3 squared times 2 squared plus x minus 5 cubed over 3 cubed times 3 squared. And it just keeps going. This is, you could look for a pattern, but there's not going to be a pattern other than that it's this. There's no reason to expect this to be anything particularly nice. But we can still ask the question, where does it define a function? So for what x's does this converge? And at the same time, for what x's does it diverge, the other set. But once you know exactly where it converges, you would know where it diverges. Of course it converges at the center. It converges at 5. It's 0 at 5. Look, you plug in x equals 5, you get 0 everywhere. The question is, does it converge any place else? And if it does, how can you tell when we don't know that it equals anything like sine of x or cosine of x? There are some general results. These results are difficult. We will not prove them, but they're cool nonetheless. So we need a definition just of an interval centered at A. So definition. So suppose r greater than or equal to 0 is an extended real number. That just means it's either a real number or it's positive infinity. So the extended means you typically allow plus or minus infinity, but then we're saying r is greater than or equal to 0, so we're only allowing the extra possibility that r is positive infinity. It's an extended real number. Then an interval centered at A interval centered at A is an interval between A minus R and A plus R. That means there are 4 choices for most R's, unless R is infinity. There are 4 choices. I want to say then an interval centered at A is an interval between A. Is an interval containing A. And you might go, well, of course, if it goes from A minus R to A plus R, it has to contain A. Well, not if R is 0 and you take an open interval. So I don't want the open interval from A to A to be an interval centered at A. The open interval from A to A is the empty set. It doesn't contain anything. Containing A. So the choices here, it means that you could have A minus R to A plus R. and not include the endpoints, but then you could include either endpoint or both endpoints. So there are typically 4 choices. If r is 0, so if r is 0, so I'll put that you could have these. If r is 0, you get an interval from a to a, and so since we want it to contain a, there's only one choice if r is 0. If r is 0, you just get the closed interval from a to a, so that contains the single point a. And if r is infinity, then going from, this would be minus infinity to infinity, that's all real numbers. So, but if r is some non-zero, it's not 0, it's not infinity, it's some positive real number, then there are 4 choices where you include or exclude either endpoint for what an interval centered at a could be. Okay, that's an interval centered at a. R equals the radius of the interval. So something like where r is a non-zero real number, you might have you might want to center at 1 and have radius 2. Well, that would mean you would go up to 3 and down by 2 over here, so down to -1. And so the interval that you're talking about is this one, or one of them. So you're talking about either the open interval from -3 to 3 or the half-open interval. You could include that endpoint, or you could include the other endpoint, or you could include both endpoints. These are 4 intervals. These are centered at 1. So you can see why it's called centered and why this is called radius. You can go that far out in either direction, right? We're looking at a is 1 here, r is 2, which means your interval goes from a minus r to a plus r. So that's from -1 to 3. Anyway, this is the picture. This is why it's called centered. All right, that's an interval centered at a. What does that have to do with anything? Well, maybe you've guessed what I'm about to say. I guess I want to try to leave this one on the board. But a power series. So this is a theorem. It's a big theorem. It's too hard for me to even give, well, I'd say give an idea of the proof. I will give us the ratio test, which will help us find the radius of intervals. And that's a hint of how you prove what I'm about to state. But the theorem is power series centered at A. Converge precisely, so this is exactly where they converge, precisely on an interval centered at A. And they diverge outside of here. That's the point of precisely. They don't converge anyplace else. Converge on an interval centered at A. I want to leave this. Then the radius of this interval, so that's the theorem, and then the definition then. That interval is called the interval of convergence, and the radius of the interval is called the radius of convergence. The interval is called the interval of convergence. and its radius is the radius of convergence. So this is a theoretical result. It tells you that when you're looking at where a power series converges, it's going to be some interval centered, for instance, this one. It will converge on some interval centered at 5. Now, if the radius of convergence is 0, that means this series converges at 5 only, because that means the interval of convergence is just the center 5. That can happen, that a power series converges only at its center. So that would be radius of convergence 0. Or the radius of convergence could be infinity, which means the interval of convergence is the whole real line, which means the power series converges everywhere, so that it defines a function with domain all real numbers. And then there's the case of you could have a finite positive interval of convergence, and then it just means that, yeah, there's some interval centered at 5 in this example. An interval centered at 5 on which this converges. We'll see that that is the case here, that there's a finite positive r radius of convergence here, and we'll see how to do that. I should say one other thing that'll be important to us later, so let me, this won't be important to us for a while, or I won't explain the significance of it later. But so suppose you've got a power series. This converges on its interval of convergence. So regardless of which of the possible 4 choices, assuming r is not 0 or infinity, which of the 4 choices you take for whether you include the endpoints or not, this is the interior, so the open interval that you get from the interval of convergence if you remove any possible endpoints from the interval. So this is the interior of the interval of convergence. If r is 0, there's nothing in it. So this open interval is the interior. Interior of an interval means, don't include the endpoints. If capital R is 0, this interior is empty. But aside from that, it's some open interval on which this power series converges. In fact, this power series does something called, it converges absolutely on the interior of the interval of convergence. So on the interior, of the interval of convergence, if you put absolute value signs around the terms, so you take the sum as k goes from 0 to infinity of the absolute value of, the product of absolute values is the absolute value of the product, so we can take the absolute value of the coefficients times the absolute values of this. This converges. The infinite series that you get, so for all the x's in the interior, when you put them in there, this infinite series converges to something. It should be unclear to you why that's important. It's a stronger form of convergence which tells us that some weird things don't happen, but we won't get to that until a few sections, until we're in the next chapter. I won't be able to explain why it's important that power series do this, have this convergence property that the sum of the absolute values of the terms converges, but it is important. And I should have stated it as part of that theorem over there. Okay, one last thing I should say. I keep writing the interval of convergence, or the interior of the interval of convergence like this. This interval is the same as, it's the set of those x's such that the absolute value of x minus a is less than r. Right? That's another, the x's that are in here, they're the ones that are within r of a. So their distance from a is less than r. Well, that's the absolute value of x minus a. It's where the absolute value of x minus a is less than r. So typically, so another thing that we're saying is power series centered at a, so in fact I should write it that way, power series centered at a, they converge where the absolute value of x minus a is less than r, and diverge where the absolute value of x minus a is greater than r. It's greater than r. Right? This is what we're saying, that this is another way of saying the same thing, that if you have a power series centered at a, then there exists an extended real number r such that the power series converges when x minus a is less than r, and diverges where the absolute value of x minus a is greater than r. Where x minus a equals r, those are the endpoints of the interval of convergence, and power series can converge or diverge there. You don't know, but certainly there's a unique real number r, the radius of convergence, that makes this true, that it converges when this absolute value is strictly less than r. That means you're on the interior of the interval of convergence. Absolute value of x minus a greater than r, it means you're outside the interval of convergence and its endpoints. So yeah, this is another and a very useful formulation of the same theorem, that the power series functions converge precisely on an interval centered at a. All right. Yeah, so this is what we saw. We saw this for the Maclaurin series of e to the x, sine of x, cosine of x, Maclaurin series for the natural log of 1 plus x, maybe. We're not sure. We saw it for maybe for the binomial series. I say maybe because for those we only really talked about when the function equals its Maclaurin series, but what I'm saying is if you take our Taylor series, our Maclaurin series for e to the x, for instance, this is centered at 0, radius of convergence, infinity. This converges on the entire real line, and then and it's centered at 0, but once the radius of convergence is infinity, regardless of where the center is, the function is the power series is converging on the whole real line. But pretending for the moment that the Maclaurin series for natural log of 1 plus x that the Maclaurin series for the natural log of 1 plus x converges only where it equals the natural log of 1 plus x, then that would tell us that that the interval of convergence for this, maybe I'll put a question mark now, we can decide later, although is from -1 to 1, which would be centered at 0. It's a Maclaurin series, so it's centered at 0. So the interval of convergence is centered at 0. The radius of convergence here would be 1. And you include that endpoint, but don't include that endpoint. Okay. All right. Meanwhile, we're back at the question of how, in any way, shape, or form, you take something bizarre like this, the sum as k goes from 1 to infinity of, just pick some coefficients, pick some formula for the coefficients in a power series centered wherever you want. How do you tell where it converges and where it doesn't? So how can you tell where this defines a function and where it doesn't? It turns out that there's pretty much one test that we use for this, or one way we determine this. There are others, but this is the primary one. It's called the ratio test. It's very nice for finding the radius of convergence. The ratio test will not tell you what happens at the endpoints of the interval of convergence. So it won't tell you about, does the interval of convergence include a minus r and a plus r or not? But it will tell you the radius of convergence. So let me state it. In the book, I wrote kind of a more general ratio test that can help in some interesting circumstances. But what I'm going to state now is how the ratio test is pretty much always used. It looks easier than the statement in the book. It's actually the second part of the statement in the book. So theorem, this is the ratio test, and we'll come back to this when we look at the more technical sections in the next chapter on a whole bunch of tests on convergence and divergence of series of constants, of numbers, instead of kind of focusing on power series. But the theorem is, suppose you have a sequence. So a sequence, bk's, where k is greater than or equal to sub m. And that bk is unequal to 0 for large k. So eventually, none of the bk's are 0. Suppose the limit as k approaches infinity of the absolute value of the kth plus first term over the kth term exists and equals L. So this is why it's called a ratio test. So right now, I'm going to do this for a series of numbers, and we're going to apply this to power series. And right now I haven't said anything about a summation. There's no infinite series here. I'm just saying I've got some sequence of terms. Eventually, they're not 0. I don't want them to be 0 when k is large because I want this limit to exist. So in fact, I could leave this out and just say this limit exists, which in particular would mean, in fact, maybe which in particular means this ratio is defined. This is called the ratio test because this is the ratio of the next term in a sequence and the term before it. Exists and equals L. Then there are cases. Then if L is less than 1, the series k goes from m to infinity of bk converges. If L is greater than 1, the series diverges. If L equals 1, the test fails. It tells you nothing. You can't conclude anything. This is called the ratio test. The ratio test for convergence and divergence. And it isn't too hard to understand what's going on here. We've looked at geometric series. In fact, we know that geometric series have a radius of convergence of 1. And what this says is, if L is less than 1, well, you should think of this, okay, when K is really big, this is less than 1. But that means if you multiply, that means that the absolute value of bk plus 1 is less than or equal to the absolute value of bk and you're multiplying by something that's less than 1. It means the b's are like a geometric series where you're multiplying, where what you multiply by each time is less than 1. But for geometric series where the multiplier, the thing you're multiplying by each time to get from one term to the next, is less than 1, those geometric series converge. So that's where, a quick idea, we will come back to this, of why the ratio test works. It's really comparing with geometric series. And if L is greater than 1, in fact, the terms that you're adding up aren't even approaching 0, so that you're adding more and more things that aren't getting close to 0. Well, so if you're adding like a whole bunch of 1s or a whole bunch of halves, an infinite number of them, it's easy to believe it diverges, as it should. And if L equals 1, the test doesn't tell you anything. So what does this have to do with anything? Here's a series. When we plug in different x's, this is a series of numbers, and we can apply the ratio test to it. And what we care about is when the limit of the ratio of successive terms is less than 1. Where it's less than 1, this will converge. Where it's greater than 1, this will diverge. When the limit equals 1, the test won't tell us anything. Well, it turns out that where the L from the ratio test equals 1 will exactly correspond to the endpoints of the interval of convergence. And that's why the ratio test, what we're about to do, doesn't tell you about convergence at the endpoints of the interval of convergence. That's exactly when the ratio test will give you a 1 for the L, and when the ratio test doesn't tell you anything. But it can tell us the radius. So I want to look at, how many examples? 4? 4, and this will be the last one. So let me write the other 3 that I want to look at. So let's look at, I want to consider 4 series and apply the ratio test. So one of them is our old friend, the Maclaurin series for e to the x. I want to see if the ratio test will tell us that the radius of convergence here is infinity, which would tell us that this converges for all x. It better, or the ratio test isn't doing what we want it to do. I'd also like to look at the sum as k goes from 0 to infinity of x plus 3 to the 2k over 7 to the k. And I want to look at the sum as k goes from 0 to infinity of k factorial times x to the k. I want to apply the ratio test to all 4 of these examples, those 3 and this one, and see what it tells us about the radius of convergence. And we'll see that the ratio test tells us nothing about the actual interval. I mean, not nothing. It tells us the radius of convergence. It won't tell us what happens at the endpoints. Before we do this, factorials come up all the time in Maclaurin series and Taylor series stuff. And because of that and the ratio test, it's important to kind of understand how factorials work with k plus 1 factorial over k factorial and things involving factorials where you look at the next term in a sequence and divide by the previous term in the sequence. I want to say again what's valuable about the ratio test. You want to know whether a series, an infinite sum, converges. And we have a test that just uses the sequence of terms, not, it's not, you don't take a limit of ratios of partial sums. That would be tough. What you take is a limit of the ratio or the absolute values of the ratios of just the terms, the summands. And those are the kind of tests we like for convergence of infinite series. We want to look at the things we're adding, the summands, the terms of the series, and have some test in terms of those that tells us whether the infinite sum converges. Of course, the definition of the sum, the infinite sum, is the limit of the partial sums, but if we could work with that, we'd just take the limit of the partial sums and get the answer. So let me look at factorials for a moment before we start in on those examples. K plus 1 factorial means k plus 1 times k minus 1 times, and you go down to times, like times 3 times 2 times 1. Great. But this part is k factorial. And so the major iteration formula for factorials is that k plus 1 factorial equals k plus 1 times k factorial. So when you're working with the ratio test and you have ratios of the kth plus first term divided by the kth term, if you encounter something like k plus 1 factorial over k factorial, don't freeze, don't think, oh, I cancel the k's, or I don't know what you might think. No, it just equals k plus 1. And it's not as though you should kind of memorize that. It should be obvious. You kind of look at k plus 1 factorial, you write out, oh, it's that, and that part's k factorial, and when I divide, you're just left with k plus 1. The reason this isn't worth memorizing is, what if you had something like 2k factorial in your sequence of terms? And so when you apply the ratio test, maybe you want to replace the k by k plus 1. So the k plus 1 term might look something like this, and then divided by 2k factorial. And then if all you've memorized is this, you'd have no idea what to do with this. How does this simplify? But just write it out, and you'll see. What do you get when you take this divided by this? Write this as 2k plus 2 factorial. And what does that mean? Well, it's 2k plus 2 times 2k plus 1. You keep subtracting 1 each time. Times 2k minus 1. So times 2k minus 1. It keeps going down to 1. And dividing by 2k factorial, 2k factorial is the part right here. So you divide by 2k factorial, that's 2k times 2k minus 1 times ... down to 1. It divides away all that stuff at the end. Oh, what happened here? It divides away all that stuff at the end, and you're left with 2k plus 2 times 2k plus 1. The point is, when you're dealing with factorials in the midst of the ratio test, don't just make up algebra rules. Just think about what factorial means. And if you write out a few things and recognize the other factorial, there's 2k factorial down there, it gets wiped out, and you're left with this. Just don't make up rules about how factorial works. Okay, so we want to see now how the ratio test applies to figuring out where power series converge, so where they define functions, points in the domain of the power series functions. So you have x to the k over k factorial. All right. So the bk, the term that we're looking at, the bk is x to the k over k factorial. Right? The thing that plays the role of bk in my statement of the ratio test. And the limit that we want to look at is the limit as k approaches infinity of the absolute value of b to the k plus 1, b sub k plus 1 divided by b sub k. If this comes out less than 1, then for those x's where this comes out less than 1, this series converges. For those x's for which this limit comes out greater than 1, that series diverges. And for x's where this limit comes out to equal 1, the ratio test tells us nothing. So this is what we want to calculate right now. And what you get is the limit as k approaches infinity of, all right, the kth plus first term. You put a k plus 1 there and a k plus 1 there. So x to the k plus 1 divided by k plus 1 factorial. And then you divide by the kth term, x to the k over k factorial. Now, one thing you should be worried about right now is, wait, in the ratio test you said the bk should not be 0 eventually. And look, when x is 0, this would be 0. So how can you do this? Yeah, the center will always, when you apply the ratio test to these, the center will always give you zeros here when k is big. But then again, we already know what happens at the center. The series converges at the center. So if you want, while you're doing this, always think, and we already know x converges at the center, so for the rest of the ratio test, we'll assume x is not the center. We already know what happens there. So when I'm writing this, assume that x is not the center, so it's not 0. And we'll see what happens at the rest of the x's. All right, now I'm going to go up the board just to be confusing. This is the limit as k approaches infinity of, you invert this and multiply, you end up with the absolute value of k factorial divided by k plus 1 factorial. And then you get x to the k plus 1 divided by x to the k. So this is times x. But as we just saw, k plus 1 factorial divided by k factorial is k plus 1. This is the reciprocal of that. So this is the limit as k approaches infinity of the absolute value of x over k plus 1. But now it doesn't matter what x is. If x is some fixed number, if x is something, as k goes to infinity, this denominator goes to infinity, this limit is 0. So what we get is that the L from the ratio test is always 0. But 0 is less than 1. And the ratio test tells us that the series with these as terms converges for any x such that this limit comes out less than 1. But 0 is less than 1. It's always less than 1. It doesn't matter what x is. So that means that this converges for all x. Right? So it means that this 0, what's relevant is that 0 is less than 1. So this converges for all x. That's the same as saying the radius of convergence is infinity. Okay, so that's good. We knew the radius of convergence was infinity, but it's just nice to see that we can get it from the ratio test. Okay, let's do this second example. So now we did that and saw that the ratio test gave us a radius of convergence of infinity. Let's look at this one. The sum as k goes from 0 to infinity of x plus 3 to the 2k over 7 to the k, and see what the radius of convergence is there, or see what the ratio test tells us about the radius of convergence. Okay, so let's look at this series. So the ratio test, you take the limit as k approaches infinity of, you take the kth plus first term, so you replace all the k's by k plus 1s. And you divide by the kth term. So that's just what's sitting there staring you in the face. So we have to look at this limit. And the series will converge for those x's for which this is less than 1. It will diverge for those x's for which this is greater than 1. And when this limit comes out to be 1, we don't know what happens, at least not by the ratio test. Again, this is centered at -3, right? The thing that makes this 0. And again, we're assuming that x is not the center, minus 3, so we're not dividing by 0. We already know what happens at minus 3. The series converges. So what do? You invert. You divide. This is 2k plus 2. You get the limit as k approaches infinity of, if you invert and multiply, you get 7 to the k divided by 7 to the k plus 1. So you get 1/7. This divides into that. You get x plus 3 squared. And you have the absolute value. We don't need absolute value signs here. And there's no reference to k anymore. Right? We invert and multiply. You get 7 to the k over 7 to the k plus 1. That's 1/7. X plus 3 to the 2k plus 2 divided by x plus 3 to the 2k, that. There's no reference to k, so this limit, as k approaches infinity, is this. This is squared. You really don't need the absolute value signs. That's not very relevant. And the question is, when is this less than 1? Right? That's what we want to know. We're trying to find where this converges, and that'll also tell us where it diverges. It converges where this is less than 1. It diverges when this is greater than 1, and we don't know what happens from the ratio test when this is greater than 1. So we want to know these things. Well, you multiply by 7 and take square roots. This is, you get convergence. Converges when, so you multiply by 7, you get this, or for divergence, you get that. And you take square roots. The square root of something squared is the absolute value. It converges when the absolute value of x plus 3 is less than the square root of 7. And it diverges when the absolute value of x plus 3 is greater than the square root of 7. But this is already written as x minus the center, minus 3. So the radius of convergence is the square root of 7. So the radius r here is the square root of 7. And we're centered at minus 3. So, this converges on, it certainly converges on the open interval centered at minus 3 of radius this. So, converges between minus 3 minus the square root of 7 and minus 3 plus the square root of 7. What we don't know from the ratio test is exactly what happens when the absolute value of x plus 3 equals the square root of 7. That's at the endpoints of this interval. But yeah, the ratio test tells us at least that this converges, or it tells us that this converges here on this open interval centered at minus 3. So there's a finite radius of convergence that's not 0. If you believe I'm giving you examples of kind of everything, one of these remaining two, so we just did this one, one of these remaining two should kind of have radius of convergence 0, and the other one, well, we'll just see. So I want to look at that series. We can do this one quickly by the ratio test. I should say that you should kind of be able to look at this series and know that it's going to diverge except at the center, because k factorial, that gets huge. As k gets bigger, it's inconceivable that this converges for anything other than the center, but you can use the ratio test. So you take a look at the limit as k goes to infinity of the kth plus first term, which is k plus 1 factorial, x to the k plus 1, over k factorial times x to the k. X to the k plus 1 divided by x to the k, x. K plus 1 factorial divided by k factorial, k plus 1. This is the limit as k approaches infinity of the absolute value of k plus 1 times x. Now, again, we shouldn't have been doing this when x is the center. We know that this converges when x is 0. If x is not 0, then this, as k goes to infinity, this goes to infinity, this absolute value goes to positive infinity. If x is not 0. Positive infinity is greater than 1. Yeah, I should have said that. The L, I said if the limit, that was actually a mistake. In the ratio test, when I stated it, I said suppose the limit of the ratios exists and equals L. I should have said exists as an extended real number. You want to allow the possibility that L comes out to be infinity. So that was a mistake when I wrote it. I should, because infinity doesn't exist. If you want to allow that, you have to say exist as an extended real number. So our L here is coming out to be infinity, which is greater than 1. We definitely want to allow that case, which is greater than 1. So this series, no matter what x is other than the center, so this series diverges for all the other x's other than the center. So this has radius of convergence 0. It converges only at the center. All right. Lastly, I want to look at this example. It's not that it's any harder than the others. It looks worse, but it's not bad. So we want to look at sum as k goes from 1 to infinity of x minus 5 to the k over 3k times k squared. Well, use the ratio test to decide where this converges and diverges, except possibly for the endpoints of the interval. So you look at the limit as k goes to infinity of the absolute value of the k plus first term. So you replace all the k's by k plus 1s. And you divide by the kth term. And you need to look at this limit. You invert, you multiply, and it helps to collect the parts of this expression that look similar. So the 3 to the k and the 3 to the k plus 1, the k squared and the k plus 1 squared, the x minus 5 to the k plus 1, the x minus 5 to the k. We get the limit as k approaches infinity. And let me write it that way. So you invert and you multiply, you'll get a 3k over a 3k plus 1. You get times a k squared over a k plus 1 squared. And then I'll write it. I won't go ahead and do the division, but I will in a second. X minus 5 to the k plus 1 over x minus 5 to the k. And then you look at what happens. This is 1/3 on the nose. No matter what k is, this is 1/3. So I'll go ahead and write that as 1/3. This, no matter what k is, as long as x isn't the center, again, this wipes out that k, and you're just left with x minus 5. This part really does depend on k, no matter what you do, but you write it in a nicer form. So you write this as k over k plus 1 quantity squared. And if you want to know what happens as k goes to infinity, it's nice to divide the numerator and denominator by k. You get the limit as k goes to infinity of the absolute value of, actually I'll bring out the absolute value of 1/3 is 1/3. This part's positive. But you divide the numerator and denominator by k, you get 1 over 1 plus 1 over k. And then times, we still need absolute value signs around the x minus 5. As k goes to infinity, 1 over k goes to 0, so this part goes to 1, and you're left with 1/3 times the absolute value of x minus 5. This is this limit. What does this tell us? It tells us that the series converges when this is less than 1. And it diverges when this is greater than 1, and when this equals 1, the ratio test doesn't tell us anything. So we get converges when this is less than 1. But you want to write that as the absolute value of x minus the center is less than some radius, some number. Multiply by 3. And what this tells you, and it'll diverge when the absolute value of x minus 5 is greater than 3. this tells us the radius of convergence is 3. And so the series converges on the open interval centered at 5. So you center at 5, you can go down 3, and you can go up 3 from 5. So it converges on the open interval from 2 to 8. Now, it might also converge at when x is 2 or 8. But it certainly diverges out when x is less than 2 and x is greater than 8, because that's when the absolute value is greater than 3. So it might converge at one of these endpoints, but we at least know that it converges on the interval from 2 to 8. So it has radius of convergence 3, and it's centered at 5. This is the first section. This is kind of the introduction to treating power series as functions. And we spent most of our time just talking about, yes, where does a power series define a function? Where the limit of the partial sums exist. And then we had the big theorem that the power series functions, their domains, so where they're defined, where they converge, form an interval centered at the center of the series. That interval could have different radii. Radius 0 means the series converges at the center only. It could have radius infinity, which means the series converges for all x. Or it could have a finite radius, which means the series converges on some interval of finite radius, and we don't know what happens at the endpoints. But how can you find the radius of convergence? In all the examples that we'll do, you'll use the ratio test. And the ratio test always gives you, for us, in our examples, will always give us the radius of convergence, but never tells you what happens at the endpoints of the interval, unless there are no endpoints, which would be, well, when r is infinity, and certainly if you get r is 0, that means the series converges only at the center. In the next section, we'll actually start doing things with power series functions, now that we've kind of spent all this time talking about when they actually define functions, how you find out points in the domain so you can say, ah, yes, there is a function here. In the next section, we're going to talk about adding them, multiplying them, substituting into them, differentiating them, integrating them, kind of why it's nice to have functions defined as power series instead of just what it means to have a function defined by power series. That'll be in the next section.